to make them match the exact numerical solution using a set of linear correction factors. These are the modified Hossein closed-form analytical approximations for the two fracturing stresses, longitudinal with red, transverse with blue, for a well drilled parallel to SH mean and perforated in the direction of SH max. Similar expressions can be derived for any well trajectory and perforation direction. These expressions are not base independent. You just need to input the in situ principal stresses, SV, SH max, and SH mean, along with the formation pore pressure PP and the formation Poisson ratio indicated by the Greek letter Ni, and you will get an equation for the variation of the longitudinal and transverse fracturing stresses against wellbore pressure. We now add to the equations these terms. These are correction factors derived using the exact numerical solutions. C_M represents the correction factor for the slope, and C_C the correction factor for the offset, which is the y-intercept. Unlike the analytical portion of the equation, the correction factors are unique for 1, a basin, 2, a fracturing stress, and 3, the perforation geometry. You change one of these three and you will need a completely different correction factor set. For a full-scale analysis of a wellbore trajectory in a given location, we have two extreme perforation directions, 2 fracturing stresses per perforation, and 2 correction factors per fracturing stress. 2 times 2 times 2 is equal to 8. Therefore, a complete correction factor set must include 8 correction factors in total, 4 C_Ms and 4 C_Cs. I named this modeling approach semi-analytical. I did not call it semi-analytical, semi-numerical, nor just semi-numerical. This is because the correction factors may not always be derived using a numerical model like I did with the one I wrote in Flag 3D. Somebody may develop a laboratory method for deriving these correction factor sets. Hence, here we have the extension attempt for this semi-analytical modeling approach over a range of stress states. We're trying to see if this is applicable over a range of stress states. To do this, we use an allowable stress state diagram. This indicates the range of stress states that are stable in the Earth's subsurface. We have SH max normalized by SV on the y-axis and SH mean normalized by SV on the x. The dotted diagonal is the line of horizontal isotropy, where SH max is equal to SH mean, and the solid dark lines are drawn using this relationship here and represent the frictional limits. Any stress state outside those bounds is virtually unstable and cannot exist, because if a fault exists under those stress states conditions, it's going to automatically lead to fault slippage, which is basically an earthquake. NF stands for normal faulting stress states, SSF strike slip faulting, and RF reverse faulting. I took the plot and within the polygon, I added some blue and red points. These indicate respectively transverse and longitudinal fracture initiation using the true three-dimensional numerical model for a specific wellbore pressure, which is 0.6 psi per foot. Because the blue region is clearly the minority, I made sure that its borders are clearly presented. Anything outside that can be assumed to be red. Then I superpose the lines that comprise the orientation criterion at this wellbore pressure. the cyan line for the stress states for which the transverse fracturing stress is equal to 0, assuming that the rock's tensile strength is 0, and the green line for the stress states for which the transverse and longitudinal fracturing stresses are equal. Both lines are corrected using the correction factor set that was developed for the Barnett Shale as shown here. As we see clearly, the blue shaded region created behind those lines, which is the criterion suggestion for transverse fracture initiation, fails to capture about half of the blue points. This proves that the semi-analytical model is not one size fits all, and caution is necessary to ensure that the appropriate correction factor set is used in each application. From the work performed in chapters 3 and 4, we know that transverse fracture initiation is harder to achieve than longitudinal. Transverse fracture initiation occurs when the breakdown pressure remains within a range called the breakdown pressure window, which is shown in yellow here, and the tensile strength of the rock is lower than the y-intercept of the blue line. This is what I call the critical tensile strength, T crit. Varying the perforation direction makes these two constraints to vary as well. Using this diagram, you can also read the fracture initiation pressure from the x-axis, which is the wellbore pressure at which the corresponding stress line crosses the black dotted line, which indicates the rock's tensile strength, again assumed to be 0. One extreme perforation direction is aligned with the smaller of the two stresses orthogonal to the wellbore, yielding the highest value of these two constraints. For the Barnett Shale, this is on the side of the borehole parallel to SH max, as I show in this diagram. This is because the SH max is smaller than SV. This is the perforation direction that promotes transverse fracture initiation best. So we call this the preferred perforation alignment, or PPA. In other extreme perforation direction, parallel to SV, both the breakdown pressure window and the critical tensile strength are minimized, making transverse fracture initiation from that perforation direction the hardest. Hence, we call this the non-preferred perforation alignment, or non-PPA. Having a perforation direction which favors fracture initiation in terms of initiation pressure and orientation provides a motivation in using perforations oriented only in one direction for promoting transverse fracture initiation at the lowest possible fracture initiation pressure. The idea of using oriented perforating strategies is not brand new, as this has been considered for sand controlling purposes from the 1970s and 80s. For a horizontal well drilled parallel to SH mean, the ideal oriented perforating strategies are either top-bottom, as we see at the top, or side-by-side, left to right, basically. I considered oriented perforating for 7 prolific shale plays, 6 from the US, the Barnett, Bakken, Fayetteville, Haynesville, Niobrara, and the Marcellus, and the Vaca Muerta shale from Argentina. 5 of those shale plays are under normal faulting stress state, and the other 2, Vaca Muerta and the Marcellus shale, are under strike-slip faulting stress state. Here we have a map on the right of that I constructed, where I colored the counties and parishes or provinces under which each shale play is located.